Alright, hi Year 12s, this is Mr. Lim here again, and this is our last video on changes of temperature for equilibrium. Then we're going to go do more stuff. Alright, so let's start. We're going to be learning really how to graph everything for changes in temperature. Alright, and then work out information from graphs as well. Alright, so let's have a look. Graphing changes, remember, you really do need to know all of your, have a deep understanding of what happens so that when you do need to graph it, it just comes naturally. So graphs, changes of rates of reaction graphs, we have to remember that both rates of reaction will spike up, okay, or will just spike up or down depending if you change temperature up or down. So both rates of reaction will change. You need to remember that the endothermic will spike up or down more than the exothermic. Okay, so the endothermic spikes up or down more. All right, then the rates of reaction will move together. Okay, so that's just your equilibrium curves until they are equal, and then dynamic equilibrium has been re-established. All right, so here's a theoretical reaction where reactants and products are in equilibrium, and then it's been shown here that delta H is equal to 92 kilojoules. Remember, you have to look at the format of this. So the colon here, or the semicolon here, indicates that it is not part of the reaction, and therefore you have to think, okay, this delta H, if it's negative, it's endothermic. So therefore the forward reaction is endothermic. Okay, so the forward reaction is endothermic. And oops, that's not look very good. Forward reaction is endo, and the reverse reaction is exo. Okay, so knowing that, we can go think about how that will look on a rate of reaction graph. So on a rate of reaction graph, you should notice that, okay, well, because they start at the same rate, or they're going at the same rate, this is a rate of reaction graph, because remember, concentration graphs don't need to do that. Then you see that, the at time whatever, the temperature increases, which causes both rates of reactions to spike up. Okay, so both blue and red go up, right? But one increases more than the other. It's the endothermic reaction is changed more than the other. And that endothermic reaction was the forward rate of reaction. Okay, so the forward rate of reaction went up, and the reverse rate of reaction also went up, but went up by less, which means that the forward rate of reaction is favored, and the forward rate of reaction is greater than the reverse rate of reaction. Okay, then they go towards each other, or the forward rate of reaction decreases and the reverse rate of reaction increases until they reach dynamic equilibrium again at this point in time. Okay, make sure that when you're drawing these, use your rulers for all of the straight line parts. Okay, and then do your best at drawing curves as best as you can. All right. Okay, so that's graphing it on a rate of reaction graph. Let's go look at it graphing on a concentration graph. So when you change the temperature, none of the concentrations will initially change. Okay, so all these concentrations will stay the same until you change temperature, and then it will start to change. The net reaction will determine which substance will increase or decrease. So let me just highlight that. Okay, so the net reaction, so that's stuff that you have to work out, will determine which one will increase or decrease. So the changes will be stoichiometric, okay, so you got to remember that. And dynamic equilibrium will be established when the concentrations no longer change at some point in time. All right, so let's have a look at this one here. Again, we have to look at how is this delta H being presented. It's presented within the reaction, which means that it's slightly different, which means that if it's on the product side, which it is, then the forward reaction is exo, and the reverse reaction is endo. Okay, the forward reaction is exo, the reverse reaction is endo, and we have a temperature decrease. Okay, so a temperature decrease, we have to think both rates of reaction will go down. So both ROR down. Which one goes down more? The endo down more than the exo. Okay, which means that the exo is favored, which means that you're going to have a net, and which one's the forward? Which one's the exo? The forward reaction. Net forward rate of reaction, which means that you're going to have more products, less reactants. Okay, so let's have a look at how that turns out in a graph. Okay, so you see here that Mr. Lim has been extra careful in making sure that I've ruled it up and used a ruler. Okay, so Both rates of reaction went down, but we don't show that because it's rate of reaction. So the endo goes down more, exo is down as well, so exo is favored. You have a net forward. Okay, so I need more products and less reactants. I can't remember which one's which. Okay, so B is a product and A is a reactant. So I'm going to have more of B and less of A. So I know that I'm going to have more of B, so let's start off with more of B. Now, the things have to change by stoichiometric amounts. And if the things have to change by stoichiometric amounts, then I have to look over here, and I have 3 B's and 2 A's. Okay, if I have 3 B's and 2 A's, that means that B is going to change by a factor of 3 and A is going to change by a factor of 2. So I'm going to make B go change up by 3, which means that it will end up somewhere around here. So I've used a ruler and looked at 3 units up, okay, and then marked a place there. And then I can draw a curve to that dot, and then I can continue it on with the ruler. Okay, then A is going to go down by 2. So where is it going to end up? It's going to end up over here on that marker. So we're going to use our ruler and we're going to line it up roughly with where the other dot was as well. Okay, it's really nice if you actually show these dots when you're doing these graphs, because then it shows your understanding. Then you draw your curve as best as you can down to that dot. And then you continue with a ruler to show that, yes, I understand, it's at equilibrium, it's not going to be changing anymore. Okay, and that's how you would graph that one, taking into account stoichiometry, working out which one is favored, which one's not, and then making sure that you use a ruler to draw it nice and neatly. Okay, then let's move on. So now we can look at identifying information from graphs. Looking at a temperature change, you can determine if a given temperature, if given the temperature, whether the net reaction what changes from in reactants and products, whether the reaction is exo or endothermic, and then if you know if it's endo or exothermic, you can work out the opposite. So it's effectively taking information from the graph and then working out stuff about the equation. So let's have a look at this graph here. Okay, so first of all, what type of graph is this? You should be able to tell that this is a concentration graph. Why? Because there's more than 2 lines and they're not the forward and reverse rate of reaction, and they don't start off equal at dynamic equilibrium. All right. So this is a concentration graph. We can see that A and C should be linked because they are both going down. So they're probably on the same side of the reaction. So I'll write it out like this, A and C, and then goes to B because B is going in the opposite direction. Okay, so here we can see that at this point in time, the temperature was increased. So if the temperature was increased, that leads us to know that the endothermic reaction is favored, right? The endothermic reaction is favored because both change and endo changes more, so therefore it changed up more. All right, so if endo is favored, that means that the reaction that produces B is endothermic. So going up here, the forward reaction, which produces B, must be endothermic, and the reverse reaction must be exothermic. All right. And also, what other information can we work out? We can work out the stoichiometry of this as well. All right. We can see that A changed by 1, so therefore that's very likely to be a coefficient of 1. B changed by 1, so that's going to be a coefficient of 1. And sorry, C changed by 1 and B changed by 3. Okay, they've actually got to be relative to each other, so you should really say that B changed 3 times as much as A, so therefore that has a coefficient of 3. And C changed the same amount as A, so therefore it's a coefficient of 1, so therefore it's a 1 to 1 to 3 ratio. All right, so that's the kind of stuff that you can work out from these graphs and how to graph them. If you have any questions, come ask, and we'll work on this in class. Adios.